Deep space. Interstellar travel. Our technology is so advanced that we have begun to travel long distances across the universe. The speed of light is no longer a problem for humans. We use it to travel through space. During the journeys we see and experience wonderful phenomena that take place in the universe. But suddenly, a black hole. This imaginary scenario is part of our fantasy that we crave so much. Man has always wanted to fly. When he succeeded in that, he wanted to explore the sky, but beyond the sky there was something much more interesting, more mysterious. The universe. The universe is full of surprises, full of mysteries. People have always wanted to understand the universe. It is a divine feeling that we humans have, and it leads us through great discoveries. One of the strangest phenomena in the universe is the black hole. Although this phenomenon was only a theory until recently, scientists have found evidence that a black hole may exist as such. The historic image of the supermassive black hole was captured by the Event Horizon Telescope, EHT, and released in April 2019. The image does not actually show a black hole, which is known for sucking up light, but rather its shadow, a glowing orange ring of ultra-hot gas. So, what is a black hole? A black hole is a location in space with such a strong gravitational field that the escape velocity exceeds the speed of light. What this means is that you require a velocity greater than the speed of light, a physical impossibility to escape the black hole, as can be seen in the image below. As no light can escape a black hole, it's black. Not black like your shirt, which does reflect light. No, since a black hole reflects no light at all, it's as black as can be. This is really quite a perfect analogy, because while we cannot study black holes directly since we cannot observe them or look inside them, we can only deduce their presence from their gravitational field which influences stars around them, and we can see radiation from infalling matter. We can study black hole analogs, and one such analog to study Hawking radiation. How is a black hole formed? It all starts with a massive star. As the star fuses hydrogen into heavier elements, a process called thermonuclear fusion, the heat produced creates an outward pressure, which acts against the inward force from gravity. In essence, the thermal pressure prevents the star from collapsing under its own gravity, and as long as the star has fuel to fuse and create heat, the thermal pressure and gravity are in balance, called hydrostatic equilibrium. At one point the star runs out of fuel, which means the thermal pressure decreases, and gravity takes over. This is when a core collapse occurs. Stars with an end mass below the Chandrasekhar limit of 1.4 times the mass of the Sun will collapse into white dwarfs. Stars with an end mass between the Chandrasekhar limit and the Tolman, Oppenheimer, Volkoff limit or TOV limit of 2-3 times the mass of the Sun will become neutron stars, and stars with an end mass above the TOV limit will become black holes. This end mass correlates with an initial mass of at least 25 times the mass of the Sun. Let's say the star in the image above is 30 solar masses. When the core collapses, an explosion occurs called a supernova, which ejects a lot of the material into space. For a star with an initial mass 30 times the mass of the Sun, its end mass is around 4 solar masses, enough to form a black hole. Here's where things get crazy. All of that material left over from the explosion, many times the mass of our Sun, falls into an infinitely small point. Black holes can form in many ways though, and large black holes can have tens to millions of times the mass of our Sun trapped in a point smaller than the tip of a pin. Some black holes trap more and more material as their mass increases. The point where all that mass is trapped is called a singularity. It may be infinitely small, but its influence is enormous. Imagine a circle with a singularity in the middle. The gravity on the inside of the circle is so strong that nothing can escape. It sucks in everything, even light. That's why it's black. This circle is known as the event horizon. An event horizon is probably what you are thinking of when you think of a black hole. What would happen, you might wonder, if we took a spacecraft near a black hole's event horizon? The answer: spaghettification. That's the technical term, at least. As our spacecraft approaches it, the gravity will be so much stronger on the side closer to the black hole than on the other side that it will get completely stretched out like a piece of spaghetti. Try as you may, you would be hard-pressed to find anything weirder or cooler than a black hole. This new visualization of a black hole illustrates how its gravity distorts our view, warping its surroundings as if seen in a carnival mirror. The visualization simulates the appearance of a black hole wherein falling matter has collected into a thin, hot structure called an accretion disk. The black hole's extreme gravity skews light emitted by different regions of the disk, producing the misshapen appearance. Bright knots constantly form and dissipate in the disk as magnetic fields wind and twist through the churning gas. Nearest the black hole, the gas orbits at close to the speed of light, while the outer portions spin a bit more slowly. This difference stretches and shears the bright knots, producing light and dark lanes in the disk. Viewed from the side, the disk looks brighter on the left than it does on the right. Glowing gas on the left side of the disk moves toward us so fast that the effects of Einstein's relativity give it a boost in brightness. The opposite happens on the right side, where gas moving away from us becomes slightly dimmer. This asymmetry disappears when we see the disk exactly face on because, from that perspective, none of the material is moving along our line of sight. Closest to the black hole, the gravitational light bending becomes so excessive that we can see the underside of the disk as a bright ring of light seemingly outlining the black hole. This so-called photon ring is composed of multiple rings, which grow progressively fainter and thinner, from light that has circled the black hole 2, 3, or even more times before escaping to reach our eyes. Because the black hole modeled in this visualization is spherical and non-rotating, the photon ring looks nearly circular and identical from any viewing angle. Inside the photon ring is the black hole's shadow, an area roughly twice the size of the event horizon, its point of no return. This visualization is mass invariant, which means it can represent a black hole of any mass. The size of the black hole's shadow is proportional to its mass, but so is the size of the accretion disk, so its properties scale accordingly. Simulations and movies like these really help us visualize what Einstein meant when he said that gravity warps the fabric of space and time. The idea of a body so massive that even light could not escape was briefly proposed by English astronomical pioneer and clergyman John Michell in a letter published in November 1784. Michel's simplistic calculations assumed such a body might have the same density as the Sun, and concluded that one would form when a star's diameter exceeds the Sun's by a factor of 500, and its surface escape velocity exceeds the usual speed of light. Michel referred to these bodies as dark stars. He correctly noted that such supermassive but non-radiating bodies might be detectable through their gravitational effects on nearby visible bodies. Scholars of the time were initially excited by the proposal that giant but invisible, dark stars might be hiding in plain view, but enthusiasm dampened when the wave-like nature of light became apparent in the early 19th century. As if light were a wave rather than a particle, it was unclear what, if any, influence gravity would have on escaping light waves. In 1915, Albert Einstein developed his theory of general relativity, having earlier shown that gravity does influence light's motion. Only a few months later, Karl Schwarzschild found a solution to the Einstein field equations, which describes the gravitational field of a point mass and a spherical mass. A few months after Schwarzschild, Johannes Droste, a student of Hendrik Lorentz, independently gave the same solution for the point mass and wrote more extensively about its properties. This solution had a peculiar behavior at what is now called the Schwarzschild radius, where it became singular, meaning that some of the terms in the Einstein equations became infinite. There are two main kinds of black holes, and the difference between them is mass. The first kind is a stellar black hole, and it occurs when a single massive star runs out of fuel. Small stellar black holes are more than 3 times the mass of our Sun. The other kind of black hole is called a supermassive black hole. These super-sized black holes are formed as the result of many black holes combining into one enormous black hole. They have millions to billions of times the mass of our Sunday. These black holes reside at the centers of galaxies and can consume other stars and gas from around their neighborhood. Throughout our universe, tucked inside galaxies far, far away, giant black holes are pairing up and merging. As the massive bodies dance around each other in close embraces, they send out gravitational waves that ripple space and time themselves, even as the waves pass right through our planet Earth. Scientists know these waves, predicted by Albert Einstein's theory of relativity, exist but have yet to directly detect one. In the race to catch the waves, one strategy called pulsar timing arrays has reached a milestone not through detecting any gravitational waves, but in revealing new information about the frequency and strength of black hole mergers. Gravitational waves, if detected, would reveal more information about black holes as well as one of the four fundamental forces of nature, gravity. As our technology advances, humans may one day be able to travel between galaxies and even use black holes as a shortcut between two destinations.